We will start with injected minority charge carrier concentration. Injected minority charge carrier concentration. Suppose we have N type of semiconductor. X is the direction of length of semiconductor. At left side X is 0 and at right side X is L. So L is the length of semiconductor. At thermal equilibrium, concentration of electrons is N naught and concentration of this is electron concentration and P naught is the hole concentration. Semiconductor is N type, so obviously N naught is greater than P naught. N naught is majority charge carrier concentration and P naught is the minority charge carrier concentration under thermal equilibrium. So at thermal equilibrium, if we draw the minority charge carrier concentration distribution with respect to length of the semiconductor, then it is constant throughout the length of semiconductor because semiconductor is at thermal equilibrium and this concentration is P naught, which is basically minority charge carriers. Now if the semiconductor is illuminated or one side of semiconductor is exposed to light or at x0 radiation falls upon the semiconductor. So at left side of semiconductor new electron hole pairs are generated and means if we consider just minority charge carrier then at left side of semiconductor more number of minority charge carriers will be there, and if we move away from the irradiated side then the concentration of minority charge carriers decreases exponentially. So we can draw this in px versus x plot. As we are moving away from x0, the concentration of holes or minority charge carriers decreases exponentially, and this part of concentration is the excess minority charge carrier concentration. Now this value is P0. At x0, excess minority charge carrier concentration is P dash 0. This excess minority charge carrier concentration is also denoted by P dash x. This is the case of low level of injection, because holes are minority charge carriers. Now we can write the expression for concentration of holes. For any exponentially rising or decaying signal, general expression is P infinity plus P of 0 minus P infinity e to the power minus x by LP. Here LP is the diffusion length for holes. Now substituting P infinity is P naught, P0 is P0 here, P infinity is P naught e to the power minus x by LP. So this is the expression for minority charge carrier concentration with respect to x. And the expression for excess minority charge carrier concentration is P dash x, and this P dash x is Px minus P naught, that is P0 minus P naught e to the power minus x by LP. Now here the excess majority charge carrier concentration is Nx minus N naught, and excess minority charge carrier concentration is Px minus P naught. The excess minority charge carrier concentration is same as the excess minority charge carrier concentration. So we can write this as N dash x is same as P dash x. Now if we differentiate this expression with respect to x, then it becomes dnx by dx, that is equal to dpx by dx. Now there is concentration difference in minority charge carriers, so there exists diffusion current. So whole diffusion current density is minus q dp dpx by dx, and whole diffusion current is now ip diffusion, that is minus q dp a dpx by dx, where a is the cross sectional area. Similarly, the electron diffusion current is plus q dnx by dx, and the electron diffusion current is q dna dnx by dx. Now from equation 4 and 5, we can write IN diffusion as Q dNA, and dnx by dx is same as dp by dx, so it is minus of IP diffusion divided by Q dp A. So the electron diffusion current is now minus dn by dp IP diffusion. See, the semiconductor is not externally connected, so the total current has to be zero, and this total current is IN diffusion plus IP diffusion, electron diffusion current plus hole diffusion current plus electron drift current plus hole drift current. Here semiconductor is N type, so obviously holes are the minority charge carriers, and drift current is proportional to the concentration of charge carriers. In this case, holes are minority charge carriers, so this hole drift current is almost negligible, so we can simply eliminate this term, and total current density is 0 because there is no external connection, so IT is 0. Now IN diffusion is minus dN by dP IP diffusion plus IP diffusion, and this electron drift current, which is because of the majority charge carriers, is NQ mu n E. So this can be written as 0 IP diffusion 1 minus dN by dP NQ mu n into E. Now this E is induced electric field that will oppose the diffusion of holes and electrons in the absence of external connection, and the expression for this electric field is E, that is 1 by NQ mu n dN by dP minus 1 into hole diffusion current. Here we have seen the minority charge carrier concentration distribution with respect to length of the semiconductor. Now suppose at t equals to 0, radiation is removed. Radiation is removed. or semiconductor is exposed to light at, it means semiconductor, the radiation is removed at t equals to 0. So now the minority charge carrier concentration with respect to time is now P of t. Under thermal equilibrium, minority charge carrier concentration is P naught, and as the radiation is removed, the concentration of holes decreases exponentially. This is P0, and again this part is excess minority charge carrier concentration. So we can write the expression for concentration of holes with respect to time, that is again P infinity plus P0 minus P infinity e to the power minus T by tau P, where tau P is now lifetime, mean lifetime of holes, and this diffusion length, diffusion constant and mean lifetime are related by this expression. LP is dP into tau P root over. So expression for concentration of holes is P naught plus P of 0 minus P naught e to the power minus T by tau P. If G is the generation rate, optical generation rate, then G into tau P is P naught minus P0, that is excess minority charge carrier concentration. So this PT is P naught plus G tau P e to the power minus T by tau P. Next, let us see what is intrinsic and extrinsic excitation. Again, this is an example of optical generation, new electron hole pair generation through light or through optical generation. If semiconductor is exposed to light or semiconductor is illuminated, intrinsic semiconductor is illuminated. All here for intrinsic semiconductor, all electrons are valence electrons and they are part of valence band, and if this semiconductor is illuminated, energy of light is h nu. If radiation falls upon the semiconductor, then electrons in valence band jump into the conduction band due to this optical energy, and this will create hole in valence band. So this is basically generation of electron hole pair through light. Now this energy of light should be greater than forbidden energy gap. Then only electron from valence band can jump into the conduction band. And this nu is c by lambda. So hc by lambda should be greater than Eg, or hc by Eg should be greater than lambda. So lambda should be less than lambda c, and this lambda c is the critical wavelength for intrinsic excitation. If wavelength of light is less than critical wavelength, then only we can generate new electron hole pairs. Now, extrinsic excitation. In extrinsic excitation, suppose we have n-type semiconductor. In n-type semiconductor, we have donor energy level, in donor energy level we have excess free electrons, and the gap between EC and ED is very small. As we have seen that this gap is around 0.05 electron volts for silicon and 0.01 electron volts for germanium. This semiconductor is illuminated. Now for silicon, this h nu should be greater than 0.05 electron volts, or h c by lambda should be greater than 0.05 electron volts, or hc by 0.05 should be greater than lambda. So this is the lambda c For silicon, lambda C is Hc by 0.05 electron volts, and for germanium, H nu should be greater than 0.01 electron volts, or Hc by lambda should be greater than 0.01. Sorry. Hc by lambda should be greater than 0.01 electron volts, or Hc by 0.01 should be greater than lambda. So this is now lambda C for germanium, that is Hc by 0.01. Critical wavelength for extrinsic excitation. Next topic is temperature dependence of mobility. Mobility mu is proportional to T to the power minus m. It means if temperature increases, then mobility decreases. At any temperature above absolute temperature, the vibrating atoms collide with electrons or holes, and that will create electron or hole scattering, and the vibrating atoms are called photons. If temperature increases, the more number of photons will be there, and that will increase the electron and hole scattering, and due to increase in electron or hole scattering, the mobility decreases. For different materials, we have different relation. Mobility of electrons mu and mobility of holes. For germanium, silicon and gallium arsenide, for germanium, mu n depends on T to the power minus 1.7 mu n, and mu p is T to the power minus 2.3. For silicon, it is T to the power minus 2.4, and for mu p it is T to the power minus 2.2. For gallium arsenide, it is T to the power minus 1, and for mu p it is T to the power minus 2.1. Now similarly we can see mobility effect of doping concentration on Mobility. Here we have mobility and doping concentration. Doping concentration is per cubic centimeter, mobility in centimeter square volt second. Ten to the power 14, 10 to the power 18, in fact it is 16, 10 to the power 18 and 10 to the power 20. $200, 400, 600, 800, 1000, 1200, 1400, 1600. This is 1400. As the doping concentration increases, mobility of electrons also decreases. Same is the case with the holes also. With increase in doping concentration, mobility of holes also decreases. Next topic is Hall effect. Hall effect is used to identify the type of semiconductor, or it is used to find out the mobility of semiconductor. In this Hall effect, we have a piece of semiconductor in the presence of magnetic field. This is semiconductor kept in the presence of magnetic field. Suppose this is P type of semiconductor. This is side 1, this is side 2. Now this semiconductor is connected with external supply, that is V applied. Side 1 and side 2 are separated by distance d, and this is the width of semiconductor W, and the product of D and W is the cross sectional area. Now current will flow from left to right because of the excitation So holes, that holes are majority charge carriers and they will move from left to right direction, or they will move from positive x direction. The magnetic field is operating in that direction. Okay, now we have moving charge particles that are holes, and they are moving in the presence of magnetic field. So there exists some force on holes due to magnetic field, and that field is FB, that is Q V cross B. Q is charge of holes, V is the velocity of holes, and B is the magnetic field. Now V is operating, holes are moving in plus x direction, moving in the direction plus x, and magnetic field is operating in z direction, plus z direction. So the direction of force on magnetic field is AX cross AZ, and AX cross AZ is minus AY. It means force is operating in the negative y direction. This is the direction of force, FB. So due to this force on holes, holes are accumulated at side 2, and the side 2 becomes positively charged. If we measure a potential between side 1 and side 2, that voltage is VH, and this voltage is positive voltage. Now as we can see, there is external connection, so holes must flow continuously from left to right side, and due to the force on holes due to magnetic field, there is the accumulation of holes at side 2. Now to oppose this accumulation of holes, an electric field is induced, and force on holes due to electric field is in the opposite direction of FB. So this will be the direction of force on holes to oppose the accumulation of holes, and this force on holes due to electric field is QE. So the total force on holes is sum of FB and FE. So QV cross B plus QE is 0. So this will give E B cross V. Here we can see the force due to electric field. The direction of force due to electric field is same as the direction of electric field. So this induced electric field, direction of this induced electric field should be same as the direction of FE. Now if semiconductor is suppose N type, if n type of semiconductor is taken, sorry, this is X, sorry, Y. The semiconductor is n type. So now electrons will flow in the direction opposite to the flow of current. This is the direction of magnetic field. Side 1, side 2. Now force on electrons due to magnetic field is now Fb, that is Q V cross B. Now charge of electron is negative, so we will use minus Q. Now the direction of B is AZ, direction of V is minus AX, or this FB can be written as Q B cross V. B is in Z direction, V is in minus AX direction. So direction of FB is AX cross AZ, and AX cross AZ is minus AY. Now again, force on electron due to magnetic field is downwards, operating in minus Y direction. So now again electric field is induced to oppose the flow of electrons, and force on electrons due to electric field will oppose FB, and this Fe is minus QE. Here I am taking minus Q because electrons are negatively charged. Again, total force on electrons is Fb plus Fe. So QB cross V minus QE is 0. So the expression for E is B cross V. That doesn't matter what is the type of semiconductor. The expression of E is always V cross B. Here Fe is minus QE, so the direction of electric field is opposite to the direction of Fe. Now if we take the potential difference between the two sides, that will give Hall voltage, and for n-type semiconductor this Hall voltage is negative. The Hall voltage is the voltage between side 1 and 2, and side 1 and 2 are separated by distance d. This will give the expression for induced electric field. We have another expression of induced electric field, that is, if I write the magnitude only, then it is B into V. B is the magnetic flux density, and V is the drift velocity of electrons or holes. Now this drift velocity, if we consider holes, then drift velocity is we have the expression for drift current density J N Q NQ V. So this V is J by not N. For holes it is P. This is PQ. Now the expression for Hall coefficient is P mu P square minus N mu N square divided by Q P mu P plus Q mu N whole square. For p-type semiconductor, concentration of holes is large as compared to concentration of electrons, so the expression of Hall coefficient is approximately 1 by QP. And for n-type semiconductor, RH is minus 1 by Qn, because n is large as compared to p. So in this expression we can write E as B J and 1 by PQ is RH for p type of semiconductor. This intensity of induced electric field is VH by D. B. J is the current density, that is I by A. So VH by D is B. I is the cross-sectional area, that is D into W. RH is 1 by QP. So the concentration of holes is B I divided by W VH Q. Now the conductivity for p-type semiconductor is P Q mu P. If conductivity of semiconductor is known, then mu P is sigma divided by PQ, and this 1 by PQ is the RH. So in this way we can find out the mobility of semiconductor.